Hello friends, I welcome you in lecture number 21 on hypothesis testing. In this lecture, we will discuss one more question on large sample test for difference of population proportions. This question was asked in GTU Summer 2021. First, we understand what is this question about. 500 units from a factory are inspected and 12 are found to be defective. 800 units from another factory are inspected and 12 are found to be defective. Can it be concluded at 5% level of significance that production at second factory is better than production in the first factory? So here this is the problem of hypothesis test for difference of two population proportions. So first we have to decide what are the population proportions under considerations, or what are the treatments which we want to compare. So here we are given the data for two factory, so we can consider factory 1 as population 1 and factory 2 as population 2. So we can consider units from factory 1 as population 1 and all the units of factory 2 as population 2. So suppose P1 is the proportion of defective units from factory 1 and P2 denotes the proportion of all defective units of factory 2, and we are given two samples. They are considering 500 units from factory 1 and they find that 12 are defective. So here we have a sample of size 500 and the number of defective units in this sample are 12. Similarly, they consider sample of size 800 from factory 2 and they find that number of defective units in this sample are 12, and we are asked to answer this question that whether we can conclude that production at second factory is better than production in first factory. So production in second factory will be better than the production in first factory if the proportion of defective items in second factory is smaller than that in the first factory. So if we can show that P2 is less than P1, then we can say that production at second factory is better than production at first factory. This P1 and P2 are the proportion of defective units in factory 1 and factory 2 respectively. So if the proportion of defective items is smaller at second factory, then we can say that second factory is better than first factory, or this we can rewrite as proportion for factory 1 is bigger than proportion at factory 2. And from this sample data we can decide sample proportions simply by using this formula. This is sample proportion for first sample denoted by P1. This is sample proportion for second sample denoted by P2 hat. So we can find out these values using this information, and now we have to apply a large sample test for difference of proportions. So for that we assume that this sampling distribution of sample proportion for each sample are normal and two samples are independent, and with those two assumptions we will use this test statistic, which is capital Z equal to P1 hat minus P2 hat divided by square root of P hat times 1 minus p hat times 1 over n1 plus 1 over n2, and we assume that null hypothesis is that these two population proportions are same, and if we assume that this null hypothesis is true, then these two values are equal, and we don't have this value, this is unknown. So for estimating this common parameter, we are using this p hat, which is given by p hat equal to x1 plus x2 divided by n1 plus n2. So we will calculate this estimator of this common population parameter, and we have all this data. Using this data, we will calculate value of test statistic, and we know that this distribution of this test statistic is normal. So we will find out z critical values using standard normal cumulative table, and then we will take our decision. So I have written all these things systematically here. We use small p1 for proportion of defective units from first factory, and we are considering a sample of size 500 from first factory, and we find that number of defective units in this sample are 12. Therefore sample proportion for first sample denoted by capital P1 hat is given by capital X1 over N1, that is 12 divided by 500, and it is 0.024. Similarly, we consider small p2 equal to proportion of defective units from second factory, and we are considering another sample from second factory which has size 800, and number of defective units in this sample are also 12. Therefore sample proportion for second sample is p2 hat equal to x2 over n2, that is 12 divided by 800, which is 0.015. and production at second factory is better than production in first factory if the proportion of defective items at second factory is smaller than the proportion of defective items at first factory. And we consider this null and alternative hypothesis. Null hypothesis always contains equality sign, so here we consider that population proportions are same, and here we consider alternative hypothesis as p2 is less than p1. Okay, this we can write as p2 is less than p1, but for deciding whether our test is right-tailed or left-tailed, we are writing p1 first here. So p1 is greater than p2, that means we have upper-tailed or right-tailed test, and level of significance is given as alpha equal to 0.05. Now to apply test statistic, we must have these two conditions satisfied. If they are not given in the question, we will assume that two samples are independent and sampling distribution of sample proportion is normal for each sample. That means these conditions are satisfied. N1 P1 is greater than 5, N1 into 1 minus P1 is greater than 5, and similarly N2 P2 is greater than 5, and N2 times 1 minus P2 is greater than 5. If all these quantities are greater than 5, then we can say that sampling distribution of sample proportion is normal for each sample, and we assume that null hypothesis is true. Therefore we have both the population proportions are equal. Suppose equal value is small p, and this is unknown, so we will estimate it using this estimator denoted by p hat, and the formula for p hat is x1 plus x2 divided by n1 plus n2. x1 and x2 both are 12, n1 is 500, n2 is 800, So we have 24 divided by 1300, and that turns out to be 0.0185. This is estimator of common population proportion denoted by small p. And once we have this p hat, we can find out value of test statistic. So remember this formula: z equal to sample proportion for first sample minus sample proportion for second sample divided by square root of this estimator p hat times 1 minus p hat times 1 over n1 plus 1 over n2. This quantity is 0.0185, and this is 1 minus this quantity, and n1 is 500, n2 is 800. We have calculated these sample proportions p1 hat and p2 hat. p2 hat is 0.015, p1 hat is 0.024, so that we substitute here, and using scientific calculator we find that value of test statistic is 1.1613, which is up to 2 decimal places 1.16. So we have this value of test statistic up to 2 decimal places. Now next step is to find out the critical values for Z, so that we can decide the rejection and non-rejection regions. Level of significance is 0.05, and we have upper tailed test, therefore we consider area of 0.05 in the right tail, and this point we denote by Z suffix 0.05, so that the area to the right side of this point is 0.05, and this is rejection region. Now we are interested in this value of Z such that area to the right side is 0.05, and this total area is always 1. So because this area to the right of Z 0.05 is 0.05, this area is 1 minus 0.05, that is 0.95. So we can say that area to the left of this point, probability that Z lies to the left side of this point, Z suffix 0.05, is 0.95. So we can decide this value using cumulative probability table for normal distribution. We have to search for 0.95 in that table, and we will be able to decide critical value. So let me open this statistical table for cumulative normal probability, and here we are interested in the value of Z such that this probability is 0.95, or we are interested in that value of Z such that area to the left of Z is 0.95, and our point Z is denoted by Z suffix 0.05 here. So we have to search for 0.95 value in this table of areas. So here you can see I have 0.9505 and 0.9495, both are equal to 0.95 if we round off up to 2 decimal places. So we will take average of corresponding Z values. Z value corresponding to this 0.9495 is 1.6 plus 0.04, that is 1.64, and Z value corresponding to this area is 1.6 plus 0.05, that is 1.65, and we take average of these two, and this is our critical value Z suffix 0.05. So I have written all these things here. We have an upper tail test, and alpha is 0.05, and area to the left of this point is 0.95. Therefore using standard normal probability table, we find that this value is 1.645, that is this point. Now we compare this critical value and value of test statistic, which is 1.16. So we can see 1.16 is smaller than 1.64. So it will be somewhere here. This is value of test statistic. That means we are in non-rejection region. So we can write that z equal to 1.16 is less than z suffix 0.05, that is 1.645. Therefore we fail to reject null hypothesis. And what is null hypothesis? Null hypothesis says that proportion of defective units for both the factory are same. So we fail to reject this null hypothesis. So we cannot conclude that production at second factory is better than production at first factory, because we are not having any sufficient evidence to reject this equality for the proportion of defective units for both the factory. So therefore we can write our answer in this way: there is no sufficient evidence to conclude that production at second factory is better than the production at first factory. So this is nice question. Here we have compared two population proportions of defective units for two factory, and for that we are using this test statistic, and we are considering this estimator for the common value of population proportions. So in this way you can answer this type of questions using large sample test for the difference of two proportions. So this is all about this session. I hope you like it. Thanks for watching.